I want to say thank you to everyone for joining. I really appreciate you making some time to talk a little bit about steel fiber reinforcing with me here today. Um, for those of you I haven't met before, my name is Claire Gandee. I'm the technical sales manager for the building products group at Beckart, and we focus primarily on the Dramix steel fiber reinforcing that we will discuss here today. Couple of kind of bookkeeping items. As I've mentioned in the chat window, please do use the chat for any questions that you have along the way. I will address as many questions as I can at the end of our session. And if we do run out of time, I'll follow back up with any remaining questions that there might be. Also, if you would like a PDH certificate for this today, please just email me and I can get you a certificate later on. So let's go ahead and kind of get started. What we will be talking about today is the technical aspects of using Dramix and steel fiber reinforcing in general. This is the second session of a four-part webinar series. The first one was a couple of weeks ago. My colleague Josh Lee presented an introduction to steel fiber reinforcing. So if you missed that, I have a link here. I can also email that to you if you want to watch the replay for that. Each one of these webinars is kind of a standalone thing, but they do really tie together and build off of each other. So if there's anything that I mentioned today that you're not really familiar with, it was likely covered last time. So feel free to reach out if you'd like a link to that replay. Oh, or we have our moderator just put that in there. Or you can always reach out to me and we can discuss. So let's jump in here. What are these things? What are Dramix steel fibers? So first things first, Dramix is the name brand for the steel fiber reinforcing that Beckart creates and provides. This is a cold drawn steel wire fiber that's known as a type 1 fiber according to ASTM A820. That was something that Josh covered in the previous session. Dramix can replace traditional reinforcement in concrete by creating a three-dimensional reinforcement throughout the concrete matrix. Within the Dramix brand, we have three different product lines: the 3D, 4D, and 5D fibers. 3D is our legacy product that's been around for about 40 years. And we've had the 4D and 5D fibers available since the last 10 years or so. The 3, 4, and 5 in the fiber name corresponds to the number of bend segments in the end anchorage. So for example, the 4D fiber has 1, 2, 3, 4 bends in the double hook end anchorage there. So that's how you could tell 3D fiber from a 4D fiber or a 5D fiber if you were just, holding it in your hand. However, there are differences in the material properties as well, specifically the carbon content and tensile strength of the steel differs between these three product lines. From the standpoint of what fiber might you expect to see in a recommendation from us, 3D and 4D fibers are most commonly used in flooring applications, slabs on grade. The 4D fibers you can think of as like a better version of 3D fibers, for lack of putting it a better way. So essentially with 4D fibers, you can often get a more optimized solution with a lower dosage for the same design. 5D fibers are going to be for your more rigorous and structural type applications. So something like a fiber only floor on piles or a structural foundation would be with the 5D fibers. And we'll come to a little bit more of the explanation between why one fiber might be appropriate in one situation versus another. Generally speaking, right, fiber reinforcing provides stress redistribution within a section. And so in order for a fiber-only solution to be appropriate, you need to use the appropriate kind of system. A statically indeterminate system has the possibility for redistributing stresses, and therefore it is compatible for a fiber-only solution to be considered. So something like a slab-on-grade is a perfect example, composite metal deck being another one. By contrast, a statically determinate system is not appropriate for a fiber-only solution. So that would be something where you might consider combining a steel fiber solution with conventional reinforcing, with PT, with rebar, whatever the case might be. So if you were to contact me about a steel fiber solution for an elevated cast-in-place concrete, a one-way beam and slab system, that would be an add to whatever conventional reinforcing you would need for strength and serviceability requirements. We would not recommend replacing any of that reinforcing or reducing the amount of continuous reinforcing in that type of application. Now, let's talk about why and what are the technical properties of this material. So, right, the people on the call here today, you are involved in structural engineering or construction generally, and therefore more than likely you already have a pretty good understanding of how concrete works and how reinforced concrete works. I will make mention of SFRC throughout the remainder of our time together here. That's a shortening of steel fiber reinforced concrete. And I would encourage you to think about SFRC as a new kind of composite material. This is something where we know how concrete behaves, we know how steel behaves, but now we have this full depth, three-dimensional reinforcement that as a composite material behaves somewhat differently than what you're used to with conventionally reinforced concrete. Now, at the end of the day, anytime you put anything into concrete, it's to add ductility to this brittle material, and steel fibers are no different. Concrete cracks. So when a crack occurs with this full depth, even distribution of fibers, you can expect a fiber to be close to that crack and arrest it immediately. Once that happens on a local level, that fiber will be engaged in tension and will anchor itself at its whatever its anchorage points. With Dramix, we have end deformations or different kinds of anchorage mechanisms out there. So in this case, right, where it anchors, it's going to develop a localized stress at that anchorage zone, which will lead to a secondary crack. That secondary crack will find another fiber, which will go through the exact same process. It will engage in tension, anchor locally, develop localized stressage, which will lead to a secondary crack, and so on and so on and so on and so forth. So I talked a moment ago about stress redistribution, and this is really the fundamental way that steel fibers work, is this redistribution of stresses throughout the system. Now, it's very important that even though all fibers generally do this, that they are very, very different in their performance. And so it's important that we understand how to characterize a fiber reinforcing and the overall fiber reinforced concrete. And not just say, oh, well, this one is 2 inches long and that one is 2 inches long, and therefore they must be equal in performance, because that's very far from the truth. So this next section of our conversation here is to discuss how do we present the performance specifications, the metrics to actually quantify how a steel fiber reinforced concrete performs, and use that as a basis for comparison to other solutions. So we have identified 5 factors which influence the performance of an SFRC. And these 5 factors are specific to the steel fibers themselves. Now, of course, we can't ignore the impact of the concrete that the fibers are within, but for the purpose of today's conversation, we'll focus only on the steel fibers themselves. So these 5 factors are the tensile strength, the anchorage mechanism, the aspect ratio, which is the length divided by the diameter, the length itself, and the collation or the distribution method of the fibers. And we'll go in through each of these in a little bit of detail. Generally speaking, the aspect ratio is important because higher aspect ratios tend to perform better, just in a generalized way. And the reason for this is because with a higher aspect ratio, you can expect to have a dense network of long fibers, because it really does come down to the network length of reinforcing. I've seen other claims of the fiber count being most important, the number of fibers, but for reasons that we'll cover in just a moment, I tend to disagree with that, because it's really the total network length. If you think about the amount of fibers being dosed into some, section of concrete, if you take each of those fibers and lay them end to end to end to end, and you have essentially a string of fiber reinforcing, if you weave that string through your section, the longer that string is the better able that section will be to resist whatever stresses develop, whether it's, flexural or shear or temperature or shrinkage or what have you. So that long network is really important. Additionally, the fiber length plays a role. Again, generally speaking, longer fibers tend to be able to achieve better anchorage, and therefore, with that better anchorage, they perform better. This plays into the same notion of why ACI 318 has minimum development length for rebar, right? That bonded rebar has to be long enough to develop its anchorage, and same thing applies with steel fibers. Of course, there are practical limitations to both the minimum and maximum lengths of fibers that you're going to put into your mix. On the minimum side, the most common application for steel fiber reinforcing in above ground applications is slabs on grade, and most often, industrial floor type applications. And those tend to have a max aggregate size of about 3/4 of an inch to maybe an inch, inch and a quarter, somewhere in that ballpark. For that, we would use a 60 millimeter fiber, which is about 2.4 inches long. And the reason for this is because you want to achieve compatibility between the fiber length and the aggregate size that's being used, because the cracks are going to tend to form in the paste between the aggregates, right? We're talking normal Portland cement concrete here, not UHPC. So UHPC is different, and there are fibers for that, and that's a separate conversation. But for this, we're talking just typical kind of applications. So we want to make sure that the fibers are long enough and oriented favorably such that they actually resist the cracking where it's likely to occur. On the maximum side, right, I said a moment ago that higher aspect ratio fibers tend to perform better. So why don't we just keep making them longer and longer? And of course, that wouldn't work in practice. There are still cases where folks are going to pump your concrete, and we want to make sure that these are pumpable. So with a 60 millimeter fiber, which is again 2.4 inches long, a 4-inch pump hose would be appropriate. So that's something to be aware of and maybe discuss at a pre-con meeting. Hey, we're using this length fiber. Let's make sure we're not using a 3-inch hose, for example. Next is the wire strength, the actual tensile strength of the steel. So your typical reinforcing grade 60 rebar, maybe grade 75 or 80 welded wire mesh. Our 3D fibers tend to be around 3 times that at 170 to 180 KSI yield strength. Our 4D fibers are up at around 230 KSI, and our 5D fibers up at 330 KSI. So you can see that the distribution of these very high strength steel elements will provide a different amount of ductility and in a different way than your traditional grade 60 rebar. If you'll notice in the graph on the right here that the 5D fiber at the top also has a significant elongation capacity, up to about 6% elongation. That's where the ductility of your SFRC with 5D fibers would come from. And that plays right into this next section, which is a discussion on the anchorage of the fibers. So knowing how something fails is an integral part of knowing how to design with it. So 3D and 4D fibers both have a similar failure mechanism. It's a controlled pull out. So these screen grabs show a single fiber anchored in what's shown as blue concrete, and where the kind of green and colored portion of that and anchorage is where that fiber has pulled out at the end of this low displacement test. So you can see that in this particular case that it's pulled out away from the edge of its initial anchorage. So the slow controlled deformation and flattening of that end hook is where the ductility of that SFRC is going to be coming from with a 3D or 4D fiber. By contrast, with 5D, it has that extra hook and that ultra high strength steel. So in this case, we actually achieve perfect anchorage, and the failure of a 5D fiber is going to be in the form of yielding of the steel itself. Again, that 330 KSI and 6% elongation capacity. It's also worth noting here that as a result of this, 5D fibers have a compatibility requirement of the strength of concrete that you're using. If you use a concrete that is too weak, then it won't be able to develop that anchorage that it's required to fail this way. So we just want to keep an eye on, using appropriate strength concrete for that fiber. And finally, the distribution. So I mentioned a few moments ago about the higher aspect ratio fibers tending to perform better. But what was also happening is that longer, thinner fibers, when they were introduced into the mix as loose, would also sometimes ball up. So Beckart took this problem very seriously and did a lot of R&D to come up with a solution to address it. And what they did was they developed a gluing solution. So in this bottom left image, you can see what's known as a clip of steel fibers. They're glued together with a water-soluble glue that as these are dosed into the wet concrete mix, so this shouldn't be one of the first components of the mix, it should be one of the last ones added. And as these are added into the mix, after about 5 minutes of mixing, the glue will start to dissolve, and each of the fibers will break off and distribute in that nice, even, consistent way that we count on. So again, it's the combination of these 5 factors of how the fibers will contribute to the SFRC performance. So it's the aspect ratio, the length, the distribution, the anchorage, and the tensile strength, all as a composite, right? Because I can't tell you how many times folks have called me and said, hey, I need a aspect ratio 65 fiber. Right, we have 3D, 4D, and 5D fibers with aspect ratio 65. We have different lengths with aspect ratio 65. So it doesn't really tell you a complete picture to just know one component of the fiber properties. So that leads us into, well, what do we do then? How do we actually evaluate and compare these things? So there is a test for it. Right? You take the steel fiber properties, your dosage, your concrete properties, you put them together, and we do deflection controlled beam tests. From this, we can extract flexural performance data. So here in the US, the most common test is the ASTM C1609. That is a test for fiber reinforcing in general. So it's not limited to steel fibers. You can see macrosynthetic fibers in there as well. And this is a beam test where you take a 6x6 by 20 inch beam section, you put it into 4-point bending, and you measure load and displacement with an LVDT. So you're going to get some kind of graphic curve that looks something like this image here in this center. Right? And in this ASTM C1609 test, you're going to extract 3 key data points: the first crack stress, or the modulus of rupture, as well as at the L/600 displacement and L/150 displacement. If you integrate under this curve, you're going to get a value known as toughness. This is from ACI 360, which is a slab on ground design guide. And if you take that toughness and average it out, divide it by the L/150 value, you'll get a value known as the EFS, the equivalent flexural strength. That's a value in PSI. And so if you have an EFS of 200 PSI, 300 PSI, whatever the case might be, now you have an actual performance metric to use as you compare to other kinds solutions. Again, this is a categorization of the post-crack flexural performance of this SFRC. Another option is to use an RE3 ratio or percentage, which is the equivalent flexural strength divided by the modulus of rupture. So that might be 30%, 40%, 50%, or the moment capacity. And it'll depend on whether you're doing an elastic analysis or a plastic analysis, which we'll come to in a few moments. But generally, that's going to be dependent on that equivalent flexural strength and this section modulus. Now, these are three of the most common performance specs that I see. They're not the only ones. There are a couple of others. So basically, we just want to pick at least one as a way to evaluate this post-crack flexural performance. And this is true of any kind of fiber reinforcing that is claiming that they have post-crack flexural properties. These are the things that you're going to be looking from. Now, if we bring this kind of around a little bit, go a little bit deeper here, there's a European test that's very similar to the C1609 test. It's the EN 14651 test. The main difference between them is that this has a notch at the center of the beam, and this is measuring crack mouth opening rather than vertical displacement. So the curve that you see in the top center here is a sample of what you might see with this. Now, if you take this and kind of simplify it into a constitutive model, you see this one in the center here. This trapezoidal shape is very important because essentially, as we are trying to understand the flexural capacity of your system, we relate it back to what we know, structural engineering 101 with our stress strain diagram for reinforced concrete. So if you remember that trapezoidal shape I just mentioned, here you see that right here for the contribution of fiber reinforcing. So now superposition applies, right? And so if you have other conventional reinforcing plus steel fibers, you can just combine the effects for your overall moment capacity, or if the fiber reinforcing is acting on its own, then you would use that contribution itself. I wanted to mention this, right? Beckard is a European company, and the vast majority of our tests and standards are based on the European approach. So that's where the derivation comes from that we use in all of our in-house tools. I can't ignore the effect of the dosage and fiber brand and performance of any individual fiber. So essentially, it's very intuitive with dosage that the more you add, you'll have better post-crack flexural performance, right? If you take the same fiber and just add more of it, these are dosed in pounds per cubic yard. If you go from 25 to 34 to 51, right, your flexural toughness, your EFS, your RE3, all of those metrics are going to increase. Of course, there are consequences to that, right? Higher dosage means more cost and maybe changes to slump and workability, things that need to be addressed. So it doesn't exist in a vacuum, but just so that you understand, it is true that when you add more, you'll have better performance. You should also note that the different fiber brands and different fiber classes do perform very differently. So on the right-hand side, if we compare the same dosage, the same length, the same aspect ratio, but change the fiber performance class. So in this case, 3D, 4D, and 5D, if we remember, the difference is the anchorage and the tensile strength. And so you notice that the post-crack performance does differ pretty significantly for many aspects being constant, but by changing those two factors, we really do see different performance. Most notably, there's two key things to extract from this. One is you'd see the modulus of rupture, the cracking stress, does not change. So just like when you add welded wire mesh or rebar to concrete, it doesn't change the modulus of rupture. That's a characteristic of the concrete itself. So we don't expect that to change with the addition of steel fibers. Secondly is the ability of the 5D fibers to achieve bending hardening behavior. So actually prior to the invention of 5D fibers, it was not thought possible that bending hardening behavior could be achieved with a steel fiber reinforcing solution. So it actually is pretty special in the market that we have that available. And that's one of the reasons why you can use 5D fibers in those really more rigorous structural applications, because bending hardening is also what rebar does as well. So to understand, what any fiber is, a correct and complete dosage and design recommendation should include the dosage as well as those 5 factors that we discussed and the concrete strength, right? So as an example, it might be 34 pounds per cubic yard of Dramix 5D 6560 BG in 4,000 PSI concrete. The understanding of what do all those numbers and letters mean, I'll just break that down for you because that can be a little bit confusing at first. So the 5D is that fiber class or fiber family. So again, I just mentioned it's the anchorage and the steel strength. The first number after that is the aspect ratio. The second number is the length in millimeters. And then the first letter is the surface finish, whether it's bright or uncoated, versus G for galvanized. And the packaging, whether it's glued or loose. So we expect anything with an aspect ratio of 65 or higher is going to be glued. Other fibers will be a loose delivery. So let's now transpose this into actual practice. What do we do with this information? So in design, one approach is just using steel fiber reinforcing for temperature and shrinkage, right? Crack control only. To do this, we go through a process to convert flexural performance, like we just discussed from the EN test, the EN 14651 test, into a corresponding axial tensile strength, because it's very hard to test concrete in tension. And so we go through a process of converting through flexural performance. And to do that, we get this equation here that nominal axial tensile strength is based on 0.37 K naught KS KC times FR4. I'm not going to go into all of the details of all of those factors, but just to say that these are basically taking into account the likelihood of positive fiber orientation in that kind of system. A slab is going to have a different type of orientation than a wall, for example. The member size factor, the structural use factor, which is essentially another safety factor if it's a true structural application. And then the FR4 is from that EN 14651 test. It's a stress corresponding to the CMOD4, that last data point in that test. And so from this, we can say, what's the tensile strength of that? I'm just picking something, a 6x6W 2.9 welded wire mesh. What's the tensile strength of that? And then we convert it through this equation to a dosage of a specific fiber. And that gives you your temperature and shrinkage dosage recommendations. If we move into the flexural applications, there's 2 main ways that we can approach this. One is to match an existing design. So let's say you come to me or somebody on my team and you say, hey, I've got a 8-inch slab with 4s at 12 at mid-depth. So we could provide an equivalent flexural capacity of a slab, but we're not going to really be able to optimize that very much. So what we prefer is to actually do an analysis. That's going to require some more design criteria, things like the loading, the joint spacing, the soil conditions, the K value of your soil, so that we can run a yield line analysis to understand more accurately the behavior of your slab and provide a more optimized solution. The reason that we use this yield line or plastic design approach, right? We all learned about yield line in our structural engineering work, for those of you structural engineers on the line, but the vast majority of our work is elastic. So this is a little bit of a departure from that typical approach. The reason we do it is on a very basic level, the plastic results most closely reflect that which we see in testing and in practice. So it's more accurate. And also because we're able to optimize the thickness of the slab and the dosage to the nearest pound, we get a more optimized solution as well. So a lot of times you can get significant economy and cost savings by going to a high performing steel fiber solution because of that. To design it in-house, we have a spreadsheet-based design tool. This is a really handy and easy to use tool. It is free, so any of you designers on the line, if you'd like a copy of this, I can set you up with it. Just reach out to me and I can get you set up and get you trained up on how to use it. Otherwise, most folks will just send us, the design criteria, and we'll just run the design and provide you with a complete calculation output so you can review all of the steps in the calculations that were done. Additionally, there is a commercial software tool out there, the Adapt Builder software, which is now part of the RISA platform. This is a finite element solution. So right back here, I'm talking about yield line with our in-house tools. The Adapt Builder solution is a finite element solution, and this has built in the Dramix reinforcing options directly for things like mat foundations, floors on piles, something where you need to get a little bit more complicated design information into your model. So what are the code implications of all of this, right? As I'm sure many of you know, right, IBC and ACI 318, these code documents do not explicitly and extensively cover the use of steel fiber reinforcing for a lot of structural applications. There are other ACI documents, 360, 544, 302, which relate to the use of steel fiber reinforcing, but these are guides and not codes. And so it really does require an additional step of having third-party testing from something like IAPMO or ICCES or UL to appropriately understand alternative materials. And specifically, both ACI and IBC allow for this. ACI 318.14 in section 1.10 explicitly states that if you have a material that is not covered within this scope of the code, that you have done testing and have evaluated it thoroughly, that you can submit that for use, and the other provisions of the code would surround that. There are other sections of the code. I'm not going to read through all of those here, but I did just kind of want to give you a sampling of some of the explicit code references in ACI 318 for the use of deformed and steel fiber reinforcing. So for example, it does call it out explicitly for shear reinforcing and other kinds of applications. IBC does essentially the same thing, allows for the use of alternative materials and processes, provided that you have that third-party independent evaluation. Again, that's going to be your ICCES or your IAPMO, which you can submit to a building official in any instance that they're questioning the use of that particular material. And that brings us to our IAPMO report number 465. This is a comprehensive evaluation for both structural and non-structural applications. So this is going to include, right, temperature and shrinkage, but also flexural shear, punching shear, and so on. It's because of this that we are in the latest Volcraft and Verco composite metal deck catalog since 2019. If you'd like to read over this document, just email me, let me know. I can email you the full document, just some light reading. It reads a lot like ACI 318 and has a lot of really good information. All right, so now let's say you're on board, you think this all sounds good, you want to start using it in your projects. So, or maybe you've been working with us for years, this is a good reminder, right? When you're putting Dramix or any kind of steel fiber in your spec, you want to include the material properties, right? That physical characteristics, but we also want to make sure to put some kind of performance spec in there. So again, that's your EFS, your RE3, your moment capacity, something to indicate your design basis, right? And I just pulled this off of another engineer specs who works with us a lot. This design is based on Beckart Dramix 4D6560BG. Contractor provides stamp calculations if you're submitting an alternate, right? Be very clear about your design basis because you worked hard on your design and you want to make sure that your design is protected. When you do add steel fiber reinforcing to your specs, it's a good idea to reference ASTM C1116, which is a standard spec for fiber reinforced concrete. That covers a lot of details, and that's a nice kind of catch-all for you, so you don't have to reinvent the wheel in your specs. On your construction documents themselves, in your general notes, plan notes, slab tags, and so on, we're really not trying to reinvent the wheel here. Generally speaking, it should be pretty straightforward. Instead of putting a 8-inch slab with number 4s at 12, you put in, a 7-inch slab with 25 pounds of, Dramix 4D 6560 BG. And in some cases, we even see folks have an alternate right on your drawings. Also perfectly fine. You might say, at contractor's option, price out this Dramix solution and let the contractor see what makes the most sense from a cost standpoint. That being said, just keep in mind as a specifier that if a contractor calls you back and says, whoa, 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 the cost of these fibers is way more expensive than the cost of rebar, just keep in mind that we really can't compare material cost. It does come down to the overall construction cost, the time and schedule savings, the labor savings associated with using a steel fiber reinforced solution can often really tip the scales in the favor of a fiber reinforced solution. So don't get hung up on just material cost. When it comes to detailing, it's important that we still use good detailing practice. For example, in an industrial floor with a structural steel framing, we're still going to recommend, isolation around the column, compressible material, rebar around that, right? Reinforcing at reentrant corners, bollards, drains, and so on. Anywhere you're likely to have stress concentrations, we're going to want to put some rebar or mesh there. And additionally, just in your detailing, be mindful of restraint. Restraint is the enemy of any slab on grade, regardless of whether it's reinforced with the best steel fibers on the barket or with, welded wire mesh. So it's important that you don't get caught up in the idea that steel fiber reinforcing is going to save the day and that you can put any kind of turn down or dowels into the perimeter of your slab and think that the steel fibers will be able to overcome that. We really do have to still minimize restraint to the extent that you can. So you were working actively to make sure that your project will be successful. When it comes to saw cutting, if you're still doing a saw cut floor, you can do that with steel fibers. The main change here is we recommend a deeper saw cut. Going to D/3 is going to help increase the likelihood that that joint is going to activate. So shallower cut might not get that full crack to develop, and then you could end up with mid-panel cracking. So we want to make sure we get a deeper saw cut. And, living in the real world here, we know that you might submit a design with Dramix, or you might receive a substitution request one way or another. So first step there, if you're unsure of what to do, I certainly recommend reaching out to us. We're happy to help you go through that process of evaluating an alternative. If it's an alternative that meets, what your initial intent was, we'll tell you so. Right? We're not going to lie about that, but we will help you go through that process. And that does also include, hopefully you have the performance characteristics in your spec. So check that, right? If you put that RE3 in there of, right, 45%, does this alternative design meet that? And don't take for granted that just because you had it in your specs that the person or group who's submitting the alternate will meet it. I don't mean to sound jaded, but it has happened before where even with a good spec, an alternative might come in that is less than that. So you can't assume that it's going to meet your initial design. And then also, look at the calculations, look at them carefully. I've seen a number of calculations from other fiber vendors that aren't always using the same information that I am. I'll put it that way. So, check the loading. Is it factored? Is it unfactored? Is it near the edge of the slab? Is it only in the middle of the panel? Check that your design criteria and concrete material properties are correct. The concrete strength, the soil K value, your modulus of rupture, all of those things are going to play a significant role. In particular, if the calculations that come to you show that they're using an elastic design approach, ACI 360, which is the slab on grade design guide, recommends a factor of safety of 1.4 to 2.0 relative to the modulus of rupture. And I've seen some really high modulus of rupture being shown, something like 12 root F prime C, which I've never heard of in real life. So you just want to take a real critical eye to that. And then take a common sense look at it, right? If you've got 30 pounds of high performing fibers in your mix and an alternative is submitted with 1 pound of microsynthetics, does it make sense? Just overall, right? I know that you might not yet have a full good feeling for fiber reinforcing, but just does it feel right? Don't be afraid to use your gut. With that, that brings us to the end here. So I see there are a couple of questions. Again, just want to quickly thank everybody for joining me today. I really appreciate you taking the time to be here with me. Please keep in mind there are 2 more webinars coming up in our series. In January, on the 20th or 21st, will be the Dramix jointless floor. So talking about reducing or eliminating saw cuts in high performance floors. And then in February, comparing to other reinforcing options. How does a Dramix solution compare to type 2 fibers or to macro synthetics and so on? And with that, let me go ahead and look here at the questions. I'm just going to take these in the order in which they were received. All right, so Ruben asks, can Dramix fiber be used for steel deck to replace the mesh? Yes, so in a composite application, absolutely. We're actually in the latest Verco and Volcraft catalog. I can email that out to you, or you can just pull it down from the Volcraft website, but I can go ahead and send you that. So absolutely, if it's being used for temperature and shrinkage only, and this is a composite application, that's a really easy substitution, and a lot of contractors prefer it because it's a lot faster. You don't have to crane all the mesh up there, and then obviously the mesh doesn't just end up at the top of the deck. Next question. I am currently working with fiber reinforced alkali activated concrete and performing 3-point bending tests, EN 14651, with Dramix 4D and 5D. Awesome. During the test, fiber rupture occurred with relative drop in applied load. Is rupture of the fiber suitable in flexural behavior, or for structural behavior, or pullout is the best mechanism to be achieved? What can cause a rupture? Can it be due to the fiber matrix interface in the right? So it's going, if a fiber ruptures, it's going to, which is absolutely possible and does happen. In fact, with the 5D fibers, if they are stressed to a point where they have that perfect anchorage and they have that 6% elongation capacity, at a certain point they are going to fail. So it's not uncommon, if it's pushed to an extreme, that could happen. Sometimes that's going to be the case. And the point is that you have a ductile failure, right? We want to see the deformation happening before that, so you have time to, make plans accordingly. So it is appropriate to use it in structural applications, but again, it might be appropriate to keep some amount of conventional or continuous reinforcing with that. It's going to really depend on the loading and the specific application. All right. Is there a minimum F prime C compressive strength for the concrete, each of the fibers, or is it dependent on the aspect ratio? Yeah, so really the only minimum that we say is with the 5D fibers to use at least 4,000 PSI concrete. It works even better with higher strength concrete. That's really the only one. You can use 3D or 4D fibers with 3,000, 3,500. That works fine. Most of the testing that we have is for either 3,000 or 4,000 PSI with those fibers. which type of fiber can be used for UHPC? So this is a topic that's come up. We used to have another fiber that has kind of been discontinued. It was called OL. Now we have a new fiber that is a 30 millimeter high strength, high carbon content fiber. It's called the BP8030 BGP, I'm pretty sure. And that is currently in development and likely to be getting a lot more traction with the UHPC sector. All right, awesome. Well, it looks like that's the end of it. I'll stick around for another minute or so if anybody else has any questions. But again, I want to thank you all so much for joining today. I hope you have a wonderful rest of your day. I'm getting all the thanks. Thumbs up, guys. You're very, very welcome. Thank you all so much. Looks like that's the end of our questions. So I'm going to go ahead and close out here. Have a great day. Thanks again.